Let's start talking a little bit about free body diagrams. Now, free body diagrams, those of you that have physics before, you probably heard somebody in physics talk about free body diagrams. Okay? You might not have understood what a free body diagram is. The problem that people have with free body diagrams is they never know quite what to draw. All right? Here's what a free body diagram is. It's just a diagram of the forces that are relevant to the body that you're looking at. And essentially what you want to do with that body is you want to isolate that body, or I like to tell people what would happen if you pull that body away from where it's supported. I've got a beam and it's attached like to bridge piers. Okay? I want to draw a free body diagram of that beam. The free body diagram is just a diagram of the forces that could act on that beam. But the first thing I want to do is I want to pull it away from where it's supported. It's supported at the bridge piers. So I take my beam and I magically pull it away from where it's supported and I plop it down on my piece of paper. Okay? The bridge beam had some forces on it. Maybe I had a truckload up here, or I had a couple loads from, whatever. Theoretically, I'm going to know those, right? But what about where it was supported? What do I have to do there? It was supported by the bridge piers, right? So don't I have to come up with some forces that represent those bridge piers? I do, right? Because that's it. Does the beam have self-weight? If it has self-weight, that's a force that acts on that beam. So, that's really what a free body diagram is. I like to think of isolating the body, cutting it away, pulling it away from where it's supported, and then putting it on your piece of paper and just in sort of a stick-like fashion, draw the forces that may act there. Now, the question comes up as to how do I represent the bridge piers? How do I represent those forces? Okay? Well, if you turn to page 63 in your book, you're going to see there's a figure there, and it's figure 3.3. And this gives you typical support conditions and how they are going to be modeled on your free body diagram. Okay? Now, again, I can take a look at some of these things. I can say, do they really happen in the real world? And the answer is, well, not perfectly maybe all the time in the real world, but some of them do. Some situations, I bet you see these. Okay? I mean, the first one is a very common one, a pin. A pin is a common idealized support. In fact, really, if I was looking at that bridge beam and the pier, I bet you one of the piers I probably draw as a pin. In fact, if you ever work on a highway and you look at how beams are really seated, you might actually see sort of a triangular type shaped steel object that sort of looks like a pin. Okay? But, I mean, it can be like that or it cannot be like that. But a pin is sort of just our idealized version of things. A pin is capable of developing two reactions. Now, I said capable of developing. I didn't say it developed. That depends on the situation. The two possible reactions that a pin is capable of creating or developing is a reaction that is normal or perpendicular to the surface, and another force that is parallel to the surface. Now again, I'll stress, it's capable of doing that. Doesn't have to do that, but it's capable of that. It does allow rotation. There is, and if you ever really get to see like a highway bridge beam, I mean, you actually will see sort of like a little pin type apparatus, maybe with a little plate on top of it that they actually have. Okay? What's another very common type of idealized support? Well, another common type of support is what they call a roller. And that's there on figure 3.3 as well, too. There's different ways you can represent this, but, you know, again, very common. A roller only has the possibility of developing one reaction force. And that reaction force is perpendicular to the surface. It's a roller, so it's allowed to roll along the, you know, if it's the ground or the pier cap or whatever I'm talking about, a roller is allowed to roll. So it's allowed to rotate, but it's also allowed to translate in this direction. And again, this is ideal. This is idealized stuff. I mean, you can make the argument, they might make the argument like in physics, well, you know, there's friction between the roller and that, so there's another force there. You know, same way with the pin. Well, this rotates, but there's some friction in the pin, so it's not complete friction-free rotation. Well, guess what, folks? We're saying that there's no friction. Things happen perfectly. That's the way it is. We've got enough to worry about without that. All right? Anybody ever see a roller, a support that looks like a roller? Yeah, I mean, a bridge actually is another good place. It might not look exactly like a roller. They actually call it a rocker, but it's a steel shoe that's got a curved plate on it. So, I mean, that thing, and you can actually see them sometimes when it's hot and cold out, that you'll see that shoe actually rotate into different positions. Ever see it in other places? How about a real simple place? You ever like do stuff maybe in your backyard or something, and you say, man, I gotta move this swing set or something, and I gotta move it from this part of the yard to that part of the yard. How am I gonna do that? And so you lift up tilt up the swing set, and you put like a log underneath of it, and then you lift up the other side, put a log underneath of it, and you start rolling it. And then when it starts to roll off the one log, you take another log, you put it in the front, you keep on rolling. You ever see anybody do that? Well, that's pretty low tech roller, but that's a roller, okay? So, yeah, we you know, it's ideal, but there are situations where we see it. The next one out there is a fixed support. Now, fixed support would be like what happens. I mean, there's a lot of fixed supports. We could talk about reinforced concrete and how many fixed supports there are, but think about a flagpole, you know? I mean, a flagpole, if the wind blows on a flagpole, the flagpole doesn't move in the direction of the wind, right? If a big bird sits on top of the flagpole doesn't sink down into the ground. So there must be reactions that occur or can occur, not have to occur, but there must be reactions that occur sort of like a pin. But when the wind blows on a flagpole, the flagpole doesn't rotate over either, does it? It doesn't flop over. I mean, if it was a pin, if I had a flagpole and I had a pin and we put lateral forces on it, what would happen? It just rotate over. But a flagpole doesn't do that, so a flagpole has to develop some rotational resistance, some moment resistance. So a fixed support actually has 3 potential reactions that occur. Or another good condition, instead of thinking about a flagpole, think about a balcony. You know, you see all these apartment buildings or condos, they have these balconies that overlook the park or the river or whatever. Those balconies just sort of jut out, don't they? Well, think about where that balcony is attached to the building. There has to be a rotate, because as you walk out on a balcony wants to rotate, right? So there has to be a rotational reaction that counteracts that. Okay? And the last one there is really a cable or a link if it was in compression. Cable is, again, another type of reaction, or has a potential reaction. And again, we see this. We see maybe a roof canopy that's supported by cables. You might even see pieces of bridges that are supported by cables and whatnot. So those are idealized support conditions, but those are the types of reactions that we would have to see as we develop our free body diagram.